Thank you for watching today's talk. My name is Amir Shahrospi. I'm a PhD student at Carnegie Mellon University's Computer Science Department, and today I'm going to present a joint work with Venkat Guruswamy and my advisor Bernard Heupler. The talk is titled as Optimally Resilient Codes for List Decoding from Insertions and Deletions. Let me start with a quick overview on the problem of coding for insertions and deletions. Consider the scenario that we have two parties, Alice and Bob, and Alice has some information in the form of end symbols out of some alphabet sigma. And she wants to communicate these symbols over a given channel to Bob, but the channel suffers from some sort of an adversarial error. So what Bob receives is not exactly equal to what Alice has sent. And the general goal is to maintain a reliable communication over such given channel. Now, this problem has been studied classically under the assumption that the kind of error that happens on the channel is a Hamming type error, meaning either erasures, symbols being turned into a question mark, or substitutions, that is, symbols being turned into another symbol out of the alphabet. But in this talk, we are concerned about synchronization type errors that are insertions and deletions. Take this string as an example. If we have two deletions at these two locations, the string would turn into the second one. And if we have two insertions at the beginning and the end of the string, the resulting string would look like this. In today's talk, we are going to talk about error correction for insertions and deletions. And error correcting codes for insertions and deletions are very similar objects to ordinary error correcting codes, except that instead of Hamming distances, we are concerned with edit distance between code words. The edit distance between two strings is simply defined as the smallest number of insertions and deletions that one needs in order to turn one into the other one. Formally speaking, an insertion-deletion code of alphabet sigma and block length n would be simply defined as a subset of sigma to the n, and the quality that we would like to have here is that the code words of this code are far apart under the edit distance metric. We define the relative distance as the normalized minimum distance of this code, and if the relative distance is high, you can correct from higher fractions of insertions and deletions. The notion of rate would be defined similarly, and a very important natural question here is that how is the trade-off between rate and distance? In other words, if you would like to have a code that has a certain minimum distance between its code words, what would be the highest rate that we can achieve? The plot would probably look something like this. At the error rate 0, you would have full information rate, but as you increase the amount of the minimum distance that you want to guarantee, the rate would drop until it gets to 0 at some point alpha 0. And this quantity alpha 0 is what we call the optimal resilience for insertion and deletion codes. That is the highest fraction of insertions and deletions that one can correct errors from while maintaining positive information rate. In this work, we are focusing on list-decodable insertion-deletion codes. In the list decoding setting, instead of expecting the decoder to uniquely identify the communicated word, we want the decoder to produce a list of up to L code words that guarantees to contain the communicated word. That would essentially translate into having no more than L code words in any ball of certain radius E. One interesting distinction between unique decoding and list decoding for insertions and deletions is that in unique decoding, there is a symmetry between insertions and deletions that does not necessarily hold in the list decoding setting. And that is, a code which is uniquely decodable from alpha fraction of insertions is also uniquely decodable from alpha fraction of deletions, and also uniquely decodable from an alpha fraction of the combination of the two, because all of these things are equivalent to having a minimum edit distance of 2 alpha n. But no such thing holds for list-decodable insertion-deletion codes. Let me give you a quick example. Consider these two strings. With two deletions, these two strings can be turned into a same string AC. And it is easy to verify that this implies that also with two insertions, one can turn both of these strings into the same string. However, this does not hold for sets of more than two strings. Let's say for these three strings, you can use two deletions to turn them into the same string, but it's easy to see that this can't be done with two insertions. For this reason, when we are talking about list decoding for insertions and deletions, we should distinguish between the fraction of insertions and deletions that are involved. And from now on, we indicate the fraction of insertions with gamma and fraction of deletions with delta. And here is a formal definition of a gamma delta L list decodable insertion deletion code. For any word x tilde, we define the function d of x tilde as the set of all code words from which x tilde can be obtained by applying gamma and insertions and delta and deletions. And with this definition, a gamma delta L list decodable code would be defined as a code for which the size of d of w for any word w is smaller than L of n. And note that L can potentially be a function of n. In the list decoding setting, the trade-off between rate and distance is characterized by a three-dimensional plot that indicates what's the largest possible achievable rate for any pair of delta and gamma that are the respective fraction of deletions and insertions. As you can see, at the point of 0, 0, where we have no errors, the maximum possible rate would be 1, and as delta and gamma increase, the rate drops. And in this setting, the error resilience is characterized by a curve that indicates where this rate distance plot hits the floor. The goal of this work is to identify the error resilience region for list decodable insertion deletion codes. In other words, we would like to identify the set of all gamma and deltas for which gamma, delta, polling, and list decodable insertion deletion codes exist. And also note that in the error resilience plot, where the curve hits the delta axis is delta 0, or error resilience for list decodable deletion codes, and where the curve hits the insertion axis indicates the error resilience for insertion only codes. Before getting to the results of this work, let's go over some of the relevant previous work and some basic bounds on error resilience. We start with error resilience for uniquely decodable codes, and we assume that the alphabet size of the code is q. With an alphabet of size q, it's easy to see that the error resilience is no larger than 1 minus 1 over q. And the reason is that with that many deletions, an adversary can basically delete all instances of all but the most frequent symbol of the alphabet, and therefore make the string that arrives at the receiving end to be the repetition of some symbol of the alphabet. And here is a list of a few known lower bounds on the error resilience for uniquely decodable insertion deletion codes. For the case of binary codes, there is a lower bound of 0.18 that is essentially obtained by a series of works on random insertion deletion codes and largest common subsequence of random strings. All in all, the state-of-the-art bounds on the error resilience for binary codes is that the error resilience is larger than 0.414. This is obtained by the work of Bukh-Ma, Bukh, and Hastad, and an upper bound of 1/2, which is basically obtained by the alphabet reduction argument mentioned earlier in this slide. Now, for list decodable codes, a very similar alphabet reduction argument would show that delta 0 is not larger than 1 minus 1 over q. Remember that delta 0 was the error resilience for deletion-only list decodable codes. For insertion-only codes, you can show that gamma 0 is not larger than q minus 1. To show this, we propose a simple strategy for the adversary. Note that with q minus 1 insertions, one can turn any symbol into the string 1, 2, 3 to q. Therefore, with n times q minus 1 many symbol insertions, the adversary can transform any given string into a repetition of 1, 2, 3 to q. For the binary case, a work of Bukh-Ma and Wang shows that error resilience is actually equal to 1/2, and a couple of very recent works imply that gamma 0 is larger than 0.707. These results are derived by a careful analysis of the size of the insertion deletion ball and providing Johnson type bounds for insertions and deletions. In this work, we precisely identify the resilience region not only for binary codes, but also for codes over any alphabet of size q. And in addition, we give explicit and efficient positive rate codes for this region. For binary codes, we show that the resilience region is equal to the area underneath the line that connects delta 0, which is equal to 1/2, and gamma 0, which is equal to 1. Note that 1 was the upper bound for gamma 0 that was obtained by the strategy that we proposed for the adversary in the previous slide. Now, for the case of larger alphabet sizes, it seems like that the natural generalization would be the area underneath the line that connects the upper bounds that we proposed for delta 0 and gamma 0, which were 1 minus 1 over q and q minus 1. However, this turns out to be incorrect. And in order to see this, consider the following scenario. Let's say delta is equal to I over q for some I between 1 and q minus 1. With this many deletions, an adversary can delete all instances of the I least frequent symbols in the alphabet. So the resulting string would be a string of length n times 1 minus delta over an alphabet of size q minus I. Now with n times 1 minus delta times q minus I minus 1 insertions, that is the size of the new string times the alphabet size minus 1, the adversary can convert this string into a repetition of the symbols of the new alphabet, as we showed in previous slides. This means that for every integer value of I between 1 and q minus 1, all of the points like this are not inside the resilience region. And in fact, these points lie on a second degree curve inside the proposed triangle. We will show in this work that, interestingly, the error resilience region is precisely the polygon that is formed by these points. Here is an illustration for alphabet size q equals to 5. Now, we give a high-level summary of how the proof works. In this video, we only talk about the proof for the binary case. The proof for the general alphabet size is slightly more technical but follows the same logic. The proof has two major steps. In the first step, we analyze codes that were introduced in the work of Bukh and Ma, which were shown to have good edit distance properties. The code words of this code are of the form of alternating repetitions of zeros and ones. That is, R0s followed by R1s followed by R0s, so on and so forth. And here we will refer to R as the period of the code word. And we would want the periods of the code words to form a geometric progression. Here is a quick example. We have 4 code words with period lengths 8, 4, 2, and 1. Note that in order to allow for a geometric increase in the period length of the code words, with a block length of n, one can only have up to O of log n many code words, and therefore the rate of these codes are very small. However, in the first step, we show that these codes provide an almost perfect error resilience, meaning that here in the binary case, the code is list decodable with list size 1 over poly epsilon from any delta fraction of deletions and gamma fraction of insertions as long as 2 delta plus gamma is smaller than 1 minus epsilon. And of course, this parameter epsilon is something that can be picked as small as one wishes to approach the perfect error resilience region. In the second step of the proof, we concatenate these Bukh-Ma codes with this list decodable insertion deletion code over large alphabets from a previous work and show that this concatenation would result into a code that has positive rate and yet maintains the almost perfect error resilience. We will use this code as an outer code in the concatenation, and a very interesting property that these codes have is that for any fraction of deletions and fraction of insertions that one picks, and note that the fraction of insertions can potentially be larger than 1, the theorem gives an efficient list decodable code for that gamma and delta over an alphabet with constant size in terms of the block length, although the alphabet size may depend on the parameter gamma. This is possible because this theorem uses list recoverable codes as an internal component, and the fraction of insertions really translate to the list sizes in the list recovery procedure. Let's start with the first part, that is the analysis of the list decodability of Bukh-Ma codes. Take some string y and assume that y is close to L code words of the code C, which is a Bukh-Ma code as described in the previous slide, and let's call those L code words x1, x2 to xl. By y being close to xi, we mean that xi can be converted to y with some number of deletions di and some number of insertions ii, such that 2 times di plus ii is not larger than n times 1 minus epsilon. In order to show that code C is list decodable with the almost perfect error resilience, we have to provide an upper bound for L. In order to do so, the paper introduces a notion called advantage that basically captures how close the string y is to a certain period r. Generally speaking, the advantage of some string to a given period ri can be a real number between -half and 1. And if the advantage is larger than some O of epsilon, it implies that y can be converted to one of the code words of the Bukh-Ma code with period ri using a small number of deletions and insertions. More precisely, di deletions and ii insertions such that 2 times di plus ii is smaller than n times 1 minus epsilon. And the larger this advantage is, the closer string y would be to a periodic string with period ri. The notion of advantage also has the following interesting property, that if you split a given string into substrings of the same length, the average of the advantages of the substrings is not smaller than the advantage of the original string. With that being said, consider the following stochastic process. Given the assumption that we have about string y, we know that the advantage between y and r1 is large. This means that there is a large common subsequence between y and x1. Now I split string y into substrings of length L1 such that L1 is much smaller than R1 and much larger than R2. Note that this is possible because we assume that the period of the code words form a geometric progression. Now, because the length of these strings are significantly smaller than R1, what would happen is that most of these substrings would be entirely projected into a run of zeros or run of ones in x1 under this large matching. And this implies that most of these substrings are either biased towards zeros or towards ones. Now I choose one of these substrings at random. That's what I call y1. And because y1 is either biased towards zeros or biased towards ones, the variance of the bias of y1 can be shown to be larger than some polynomial in terms of epsilon. And the bias is defined formally as the number of ones in y1 minus the number of zeros in y1 divided by the length of y1. Now the next step of the stochastic process is to repeat the same thing between y1 and x2. Again, we split y1 into substrings of length L2 so that L2 is much larger than R3 but much smaller than R2. And because of this quality here, we know that the expected advantage of y1 to R2 is large. So the same sort of argument can be repeated to show that now the variance of the bias of y2 is even larger than the variance of the bias of y1 plus an additional term of omega epsilon to the 3. We can repeat this nested subsampling procedure L times, and what we would end up with is that the variance of the bias of the substrings in the last level is at least L times omega of epsilon to the 3. Now, note that given the definition of the bias, this quantity is somewhere between 1 and minus 1. This means that the lower bound of L times omega of epsilon 3 can never exceed 1. And this would provide an upper bound of O of 1 over epsilon to the 3 for L, that is the list size of the code. We now give an overview on how our rate-boosting code concatenation scheme works. In our concatenation scheme, we pick an instance of this large alphabet insertion deletion code as the outer code and use Bukh-Ma codes as the inner code, with parameter epsilon in, that is some O of epsilon. The construction of the code is like the classic code concatenation, which is for any code word of the outer code, we replace each symbol with its corresponding code word from the inner code and write these back to back. The resulting string would be a code word of the concatenated code. But the decoder is slightly different from code concatenation schemes that have been proposed in the previous work. For the decoding, we use a sliding window that is almost twice the size of the inner code, and give the elements in this window to the decoder of the inner code to produce a list of symbols within the alphabet of the outer code. We shift this sliding window O of n epsilon steps and repeat this procedure to the end. This would result in a string that is of length an in times an out times the list size of the inner code of symbols out of the outer code. And the eventual output of the decoder would be the decoder of the outer code given this resulting string as the input. And the reason that this works is that given that we know the number of insertions plus twice the number of deletions that happen in the channel is smaller than 1 minus epsilon times the length of the channel, for most of the code words of the inner code, this also holds true. This means that most of the code words of the inner code would appear in an instance of the sliding window decoding. And therefore the eventual string would contain an adequately large substring with the initial string x1, x2 to x and out. The Final point that I'd like to emphasize here is that, as you can see here, we have the x tilde vector, which is significantly larger than the x vector. And we're using the guarantee that these two vectors have an adequately large common subsequence. So for the decoder of the outer code to contain the vector x, we need the outer code to be one that is resilient against a fairly large fraction of insertions, that is, n times ln. And this is where the codes from the theorem in the green box would come to help, because they enable us to encode from arbitrarily large fractions of insertions. Here is a brief summary of the results of our work. Thank you for watching this video.